Good morning, everyone. My name is Steve Hale. I'm a Senior Engineering Manager here at CAE Associates. Today I'm going to present Workbench Topology Optimization. This is part of our ANSYS e-learning series. And I'll be talking for about 25 minutes. Everyone is muted, so if you do have any questions, please type those into the chat window, and I can address those at the end. Okay. Let me give you a little background about who we are. We're an engineering consulting firm here in Middlebury, Connecticut. We specialize in finite element analysis and CFD analysis, and we do tech support and training with the ANSYS software. We've been an ANSYS channel partner since 1985, we have developed the ANSYS e-learning series to provide demonstrations of very useful ANSYS capabilities and features so that you can maximize your software investment. I recommend that you check out our website. It's at caeai.com. We have an extensive resource library of useful technical information. We have on that part of the site, we have papers and case studies, demonstrations, webinars, etc. And you can access all our older e-learning webinars on that part of the site. In addition, we have our Engineering Advantage blog. Every week we put out a blog article, and the vast majority of those are technical articles, and there's some extremely useful information in those as well. In terms of our training classes, you can check out our training calendar and register for our classes directly from that calendar site. If you have any questions about what classes to take, I recommend that you check out our CAE University link, and that has a description of all our classes, and it'll help you decide which training classes are best for your needs. As I mentioned, you can access all of our older e-learning videos from the resource library on our site, or you can go to our YouTube channel, youtube.com/CAEAI, and on there you can access all of those older e-learning demonstrations. Okay, so let's move on to the technical part of the presentation. As I said, I'm going to talk about ANSYS Workbench Topology Optimization, talk about why you might want to use it and how it works, and then I'll go through a demonstration problem. So what is it? Well, it's a design tool for determining shapes that can satisfy design criteria while minimizing or maximizing an objective. And those objectives can be anything from minimizing mass or volume. You can minimize compliance, which maximizes stiffness, or you could maximize the natural frequencies. So if you want your natural frequencies to be above a certain value, you can certainly include that. Here's a example down at the bottom of a control arm structure. You start off with a block of material that has an approximate shape. You have to make it oversized to define the allowable boundaries of the part. Then you run it through the optimizer with your optimization objective and a series of design constraints. It comes up with a distribution of material by removing material from the main block of material. And then from that, you can do a validation where you take that geometry in STL format, and you can effectively reverse engineer it to create a dimension part, which you see down in the lower right. So why would you want to use it? Well, it helps you to create initial design concepts if you don't already have one, and you can come up with some quite novel design concepts that are both lightweight and stiff. It ensures that design criteria are satisfied. So, of course, you may have some design constraints where you want to make sure that you're not exceeding a certain stress, for example, or a certain deflection in different parts of the model. And you can add those constraints as well to the optimization study. So how does it work? Well, it finds the best distribution of material given an optimization goal and a set of constraints. Specifically, it takes a solid mass of material in any shape that you want to define, and it removes that material to achieve the following, which would be to minimize or maximize your optimization objective. And then it also satisfies a set of constraints that you define, such as maximum stress, displacement, or natural frequency. So here's an example of a pressure vessel, or really more of a pipe segment. We have an internal pressure on that segment. The original geometry is defined as just a very simple straight pipe on the left. In this case, the objective is to minimize compliance, which maximizes stiffness, with the following two constraints. Mass reduction, in this case you want to be greater than 40%, and then max equivalent stress less than 10,000 psi. So what we get is the optimized, after you run it through the optimizer, you get the optimized shape that you see on the right. The max total deformation is about 2 times what you obtained with the original flat geometry, but the mass reduction is 42%, so that's quite significant. And the max equivalent stress is still, you see, its optimized value is less than the 10,000 psi limit that you defined as a constraint. So the design constraints themselves can be one of the following. You can limit the maximum mass or volume to a certain value. You can limit the maximum equivalent stress. You can limit the minimum natural frequencies for a mode or range of modes. And then you can limit the maximum displacement at a specific node. You can also limit the maximum reaction force at the constraint locations. Okay, so let's go straight into the demo problem here. What we have is we want to design a linkage mechanism. In this case, as an example, I took the a linkage as part of a robotic arm, and but this would really apply to any linkage mechanism or support structure. The objective is to minimize the mass with the following constraints: maximum equivalent stress of less than 200 megapascals, maximum vertical displacement at the right side. So you'll see the loads on this part are a 500 Newton load on the right side hole, and then the left side hole is fixed. So the constraint is to limit that max vertical displacement on the right side to 0.5 millimeters. And then also we want to make sure that the minimum natural frequency in that vertical direction is greater than 800 hertz. Okay, so let's jump into project page here, and we'll look at the 2 analysis systems that you see at the bottom. We have a static structural system and a modal system, and those 2 systems are set up to be defined or defined on the original block, solid block of material. So we have a fixed support on the left side, remote force applied to the right side. You can solve this to get the starting deformations and stresses for this solid block of material. In addition, we have to include a modal analysis because we're going to set a natural frequency constraint to be greater than 800 hertz. So we have our natural frequency solution here on the original block. Now to run the topology optimization, go over to the toolbox of analysis systems. We drag and drop topology optimization onto the solution item of the static structural system. And we also have to link the solution item from the modal system to the setup cell of the topology optimization system. So now those solution cells for both static structural and modal are linked to the topology optimization. We go back into mechanical, we now have a solution folder for, or analysis system folder for topology optimization. The first item we can look at is the optimization region. This is the region or the volume that's going to be optimized. So this is the volume or the part of the mesh that's going to be carved away to create the optimized design. Now in this case, we've applied it to all bodies. Now the exclusion region has to be the boundary conditions because we can't remove material from the locations where the boundary conditions and the loads are applied. So that's what we see in red. Let's move on to objective. Objective appears as a table, and right now we have objectives defined for the two analysis systems, one being compliance for the static structural system, which we have under environment name, and then the other one for the modal system. I'm not going to optimize on the modal system, so I'll uncheck that. I am going to optimize on the static structural system, but I'm going to change it from compliance to mass, and I want to minimize the mass in that case. Now let's take a look at the response constraint. So this is the design constraints that we want to apply to our system. And the first one we want to set is global von Mises stress. If you recall, I want to set that to a maximum of 200 megapascals. I can insert other design constraints as well. So I'll right-click on Topology Optimization, Insert, and I want to set a displacement constraint in the right side hole where the load is applied. So to do this, I have to actually apply it to a node point. So I change the selection criteria to node point. Zoom in here and pick any node in that hole. Pick this node, apply that pick, and then I'm going to set the maximum deflection there to 0.5 millimeters. Okay, let's apply another constraint. In this case, I want to apply it to the natural frequencies. And the mode number that I want to constrain is the second mode. The second mode is the vertical bending mode. And we can determine that by looking at the modal solution. You can see that's the vertical first bending mode. That's mode 2. So I'm going to constrain mode 2 to have a minimum frequency of 800 hertz. We also have to define a maximum frequency. Now, in this case, I don't really care what that is, so I'll just set that to a high value of 10,000 hertz. Now, there are a couple other things we can do with this. We can actually set some manufacturing constraints. So I'll right-click and insert member size. So member size that means that I'm going to limit the size of the optimized members to a certain value. So I'll set this to 8 millimeters. That means that the cross section, in this case, of the member can be 8 millimeters or larger. I can set one additional manufacturing constraint. In this case, I'm going to use the extrusion option. And what this does, if I set this to x-axis, it means that the cross-section of the optimized geometry will be consistent or constant in that x direction. So that's useful if you want to create a optimized structure that can be extruded, or in this case, I want to use it for metal cutting. So I want a consistent topology in that global x direction. Or I can use any coordinate system that I want. So there's another coordinate system defined called symmetry. I can use that as well. Now the x direction is parallel to the global x direction, so it doesn't matter in this case whether I choose the global coordinate system or the symmetry coordinate system. Okay, so now the topology optimization is completely defined. I can solve it, so let me go to the solve system because it takes about, in this case, about 10 to 12 minutes to solve. So let me open that up. Okay. So this is the optimized geometry. You can see that the topology is consistent in that global x direction. There are three colors that are defined here, which define what we call topology density, which really just shows you the distribution of the optimized material. And you can see you have this color for remove, marginal, and keep. So it's keep, that means that you have to keep that material. That's all in the dark gray. And then marginal is in the lighter gray, remove is in red. So I do have some red material in here. And we can look at the distribution also by scrolling the retained threshold to the left or to the right to a lower number or a higher number. Now, if the number is lower, it represents a more conservative design. If the number is higher, it represents a less conservative design. Now, if you get up to a value that's too high, then you'll see that you lose some of the material that you really need to distribute the load throughout this structure. So you can tell, I can tell right away that this is not going to be a viable design. I need to go to a lower, more conservative structure. So around here might be a viable design. In my case, I'm going to go down to about 0.33, and that represents a more conservative design. Okay. Now, this is showing the distribution of material. I can't get stresses and natural frequencies directly from this topology density value. So what I have to do is take or create an STL geometry from this, bring it back into a static structural modal analysis, and then perform those analyses to verify the final design. So this is done by right-clicking on Topology Optimization Solution. You can transfer this to a design validation system. So we can see that up here in these link systems, where the result is linked to the geometry. And this is a space claim cell. And the space claim allows us to take the STL geometry, and from that we can recreate dimension geometry. So let me quickly open space claim here. And you can see this is the STL geometry that gets imported. I created a plane through the center of this so that I can extract the curves that represent the boundaries of this geometry. So I can click on Extract Curves. From that, I have the curves that represent those boundaries. Then I have to create a surface, and I can pull that surface to create the 3D part. So now I've created a surface. If I pull that surface, you notice it doesn't have the holes in there. let me undo that. What I need to do is cut out the holes. Now I should be able to pull on that geometry. Okay, wait a second. Don't think I cut that out. Try that again. Not quite working as I want it to. But let's take a look at, oh, there we go. This geometry here, which I created previously. And here you can see that we have the three-dimensional part, and I added a sketch to define an arc at the left side, and I smoothed out this geometry here on the right side a little bit as well. Okay, let me close out of Workbench, or out of Space Claim. Open up this static structural system, which contains the new optimized geometry. I have a mesh defined here. The nice thing about this validation system is that the constraints and the remote forces are already applied. I can solve that. And you notice I also have a link system for the modal analysis. When I solve this, I get a peak deflection of 0.31 millimeters, which is less than my constraint of 0.5 millimeters. I also have a max equivalent of stress of 83.4 megapascals, which is quite a bit less than my constraint of 200 megapascals. The modal analysis, let's take a look at that. I can solve that quickly. The second mode is the bending mode in the vertical direction. That has a natural frequency of 1007 hertz, which is quite a bit higher than my constraint or my design criteria of 800 hertz. Okay. I want to go back to the presentation here. And this is a summary of the optimized solution. The mass reduction is considerable. The mass reduction is 52%. And the max equivalent stress, 83.4, max vertical deflection, 0.31 millimeters, and the mode 2 natural frequency is 1007 hertz. We could also go back, if we wanted to, we could evaluate less conservative designs. So the design that we looked at and evaluated or validated gives us 52% mass reduction. We could also go down to about 60% mass reduction, which is what we see here at the bottom. You can see that has these support members in red that we see up here are removed. And in Space Claim, we could smooth out these curves quite a bit and make smoother cutouts. Okay, to wrap this up, topology optimization is available with all ANSYS mechanical licenses. It's included in Workbench versions 18.0 and higher. Prior to that, it was supplied as an ACT extension, and you can download those versions from the ANSYS customer portal. Extensive help is included in the ANSYS help system, and it is relatively easy to use, and it can lead to some very novel and unique design concepts.